Hey everyone, welcome back. Today we're going to talk about linear regression, which is the first of the machine learning models that we're going to cover in this class. Whenever we talk about these models, we're going to talk about the 5 questions. And this kind of goes back to, we're going to approach these models going back to the ideas that were brought forth in that paper by Bremen. All right, so the 5 questions, what are they? What does this model do? What are the inputs? What are the outputs? How can we measure the performance of this model, and how can it fail? All right, so what does it do? So to use linear regression, what we're going to do is we're going to create a linear model that predicts a continuous output value based on inputs. So let me explain that a little bit. We're going to have X, the input matrix here, which is going to have all of our observations. We're going to feed that into our linear model, and it's going to output some value that it predicts based on the inputs. So then the question is really, how does the computer find some equation, some linear equation, um, such that it estimates the very best output value given a bunch of inputs? Well, luckily, we're not going to have to worry about that too much because the computer is, for the most part, going to handle that. But we're going to learn a lot about how that happens. And that's going to be defined and described much better than I could do it by Andrew Ng in the videos that I included in the course. So, okay, what are the inputs? What does an input look like? Well, so a single observation's input is going to be consisting of scaled numerical values. So, for example, maybe I would have 3 values, x1, x2, and x3, such that x1 is equal to 0.5, x2 is equal to 0.2, and x3 is equal to 0.7. Okay, but there's two problems with that. What does scaled mean? I haven't really defined that term yet. And then also, how do we convert categorical variables to numbers? If you remember back to the Titanic data set, we had categories. And so how do you get a category to a number? We'll talk about that in a second. First, let's talk quickly about scaled. Okay, what scaled means is that we want all of the variables to be about the same scale or magnitude. And a really easy way to do that is to use z-score, which is something that we would use in statistics if we were converting between two different normally distributed populations. If you're not familiar with z-score, that's okay. It's pretty easy. All you do is you take your original input value, you subtract the mean, and you divide by the standard deviation. So what that gets you is that gets you a new score, z, which has an average of 0 and a standard deviation of 1. So everything is on the same magnitude. And that's really good because if you have one variable that's, say, in the thousands and another variable that's very, very small, 0.1 or 0.2, that's a really bad thing for linear regression. And so we want to fix that by scaling all of the variables to be about the same size. All right, the next thing we need is we need our values to all be numerical. Computers aren't so great at understanding words like male and female. So we already know how to convert text to numerical features. We did that last week with TF-IDF. And continuous variables are easy enough, but categorical variables, we haven't really talked about that yet. That's okay, it's not very hard. Consider the sex category from Titanic. What we can do, easily enough, is just change that category so that every time we see female, we put a 1 in the column, and every time we see male, we put a 0 in the column. And so really what that does is it transforms that variable into an indicator of female. So 1 is present if female, 0 is present if male. All of a sudden, we've gone from a word category to a numeric category, and that works pretty good. There's one thing that makes it a little bit trickier, though, and that's when we have complex categories. So let's go back to the Titanic example again. In Titanic, we also had another variable called passenger class. And passenger class could belong to either passenger class 1, 2, or 3. So then what do? We can't just use 0 or 1. So it's actually not too bad. What we do is we create 3 new variables, and we'll call those variables P class 1, P class 2, and P class 3. And then it's as simple as if we had a passenger that was passenger class 2, putting a 1 in the 2 column and a 0 in the 1 column and the 3 column. And so all 3 of these combined would indicate that it's passenger class 2. One thing that we can do to make this just a little bit better is we can drop one of these classes, because we can actually represent all 3 classes using only 2 variables. So for example, if passenger class 2 and passenger class 3 were both not true, 0, then we knew that it really is passenger class 1, which has been removed. This technique is called one-hot encoding. That's what us computer scientists call it. If you're a math person, you may call it something else, like an indicator variable or a dummy variable. It's all the same thing. Okay, so what are the outputs of a linear regression? The output is going to be a continuous value that we want to predict. Something like house price, maybe, which we're going to do in the homework, or the cost of a car, or the cost of the computers based on their features. All of these things, when we're trying to predict a continuous value, that's a regression problem, not classification. And that's really just the only important distinction. Okay, so let's say we've let the computer build some linear model using the inputs that we've talked about and the outputs that we've talked about. How do we know if that model is a good model? Well, so this is where we need to talk about model performance. We've already talked a little bit about a holdout set, and that's the idea of a test and train split. And just to recap there, what we're going to do is we're going to take our historical data that we're going to use to train our algorithm, and we're going to take just a little bit of that data, and we're going to take it and split it off and hold it aside. And then later on, once the algorithm has been trained by the training set, we're going to use the test set to test and see how accurate our algorithm is. So for the test, we know the dependent variable, but we're going to hide it away from the computer. So let's call that y. We're going to show the computer our input variables, our independent variables, and let it predict y, the dependent variable. Let's call the predicted variable, so what comes out of the computer, y hat. This little thing here is called a hat. Okay, so then to predict or to compare performance or to estimate performance, we're going to compare y and y hat. The metrics that we use to compare the two are going to be RMSE, which is root mean squared error, and the coefficient of determination. And I'm going to cover that more in another video in just a minute. So lastly, one last thing on our introduction to linear regression. How can it fail? What can go wrong? Well, there's a huge assumption in linear regression, and that's that the problem that we're trying to solve is linear. Maybe it's not. If it's not, that's okay. We can adjust that by adding polynomial terms manually. But this opens up the potential for overfitting. And there's an entire video on this from Andrew Ng, so I'm not going to cover that. But please do watch that video and be very familiar about what the difference between bias and variance is and how to manage those two things. The other thing that can go wrong is a linear model assumes that the data is independent and identically distributed, IID. It's a commonly used statistical abbreviation. And that might not be true. And sometimes that's not a problem. Sometimes it is a problem. To learn more about this, you'd want to read the Gauss-Markov assumptions for the best linear unbiased estimator. Yeah, so I'll tell you, this is an important concept in statistics, and this is a rule that we commonly break in data science. We can usually get away with it because our n is very, very large. We kind of tend to deal in the big data space, but we can't always get away with it. That said, if the model is useful and if it validates well, then we can break that rule. And rules are meant to be broken. All right, I hope you enjoyed this introduction. Please watch all the Andrew Ng videos. I think you'll enjoy them too.